Now we want to show that the eigenvalues phi will form a orthonormal set for this normal matrices, and so we'll follow the textbook using this x sub I or x sub j as the eigenvectors for I or j, and then we do a scalar product of x sub j with a operate on x sub I, and obviously I'm not totally using the Dirac notation. We don't have the other vertical lines, but anyways, just the same. So this a operator x sub I using this notation will give you the eigenvalue lambda sub I. And then the lambda sub I, you can take that out from the scalar product, become lambda sub I times x sub j, and the scalar product between x sub j and x sub I. So that is this equation. And now we do the same thing for the adjoint operator, but we reverse the I and j, so x sub I and scalar product with a deck x sub j. Well, then using this, what we just derived, the eigenvalues of a deck x sub j is just the complex conjugate of lambda sub j, just using this result that we derived. And that, so we can write like lambda sub j complex conjugate, the scalar product x sub I and x sub j. Okay. And now we want to put the left hand side actually of the same form as the first equation. There's a different way to do it, different trick that we can try to make it of the same form. And one thing we can do is just use um, the definition of the uh, adjoint operator and move the adjoint to the left hand side, because now the adjoint of the adjoint is just A itself. Go back to, so A operate on x sub I and take the scalar product of x sub j. Okay. And well, one thing that we will get is x operate on x sub I will give you lambda sub I. And then that is in the left hand side, so it will be lambda sub I complex conjugate and scalar product between x sub I and x sub j. I mean, uh, this is the correct result, but we probably don't need this equation later. So we instead we continue with this form, and we use the property of scalar product. So we reverse the order of the left and right slot and write x sub j and scalar product with a operate on x sub I. And then the whole thing, you take the complex conjugate. Okay, so that's just the basic property of the scalar product. Now we use the uh, the the eigenvalue of this, the x a operate on x sub I become lambda sub I. You can take that out, and then you get lambda sub I. Actually, what we do is going back to this equation. So because we are taking the complex conjugate, and now we take the complex conjugate of this that equation. So that will give you the lambda sub j, and then the complex conjugate of the scalar product just reverse x sub I, x sub j. And now you see that the left-hand side of the same form of the first equations, and then the right-hand side is not, so you can subtract the left-hand side equals to 0. The right-hand side is subtracting x sub I and x sub j multiplied by scalar product xj, x sub j and x sub I. That equals to 0. So as long as lambda I is not equal to lambda j, then we have the scalar product x sub I, x sub j equals to 0. Obviously, we assume that the I and j, they are non-degenerate, then the eigenvalues are not the same, so x sub I, x sub j is 0. And we can extend that to a degenerate case also by using the Gram-Schmidt method. So by choosing by our choice, then we can choose x sub I, x sub j equals the Kronecker delta. So we can choose a set of x sub I that form a orthonormal set. And so this is the way to derive that. It's similar to what we did for the Hermitian operator, and but this is for the normal matrix, and they still have the same property that the eigenvalues form of a normal set. And just like the Hermitian operator, we can use this set of orthonormal operator to diagonalize the operator. And now we can repeat the argument. Now there are two set of equations. The first line of equation is one equation, and then start from the second line. Actually, is just a single equation. So the first one is the first line is one equation. The second line is all the equal sign equals to that the same form. We get to the form that the left hand side is the same x sub j and scalar product a operator x sub I, but the left hand side not, and one is multiplied by lambda sub I, the other is multiplied by lambda sub j, and then we can subtract the first equation with the second equation, which is the last line, and then finally by this two equation we get to the final equation that lambda sub I minus lambda sub j and multiplied by the scalar product with x sub j and x sub I equals to 0. And then with normalization of the eigenvector, we can define a set of orthonormal eigenfunction and get to this orthonormal condition. And now with this orthonormal set, we can diagonalize the operator both A and A dagger, but the differences, the eigenvalues may not be real, because we showed that the A dagger and A, the eigenvalues are complex conjugate to each other. They're not exactly the same, so they may not be real. And the only thing is that they still form a orthonormal set, and you use this eigenvalue to diagonalize both matrices, and we can do the same thing just like the Hermitian operator, and come up with the form. And the form is just well, after you apply the transformation matrix using this set of orthonormal eigenvectors, then we can get to the diagonal form of the matrices, and the then the diagonal values are these eigenvalues of the A operators lambda, as well as for A dagger you get an eigenvalues lambda complex conjugate. Say you can write in say a matrix with only diagonal lines lambda 1, lambda 2 to lambda n for A. But for A dagger, now they are not the same. So, but they're still diagonal line with the same unitary matrix. So you have the matrix is of the similar form, but the diagonal lines are slightly different. So instead of lambda, you get the lambda complex conjugate, and the unitary matrix that we form is like what we discussed before, just the eigenvector as column vector and put it together and say x sub 1, x sub 2, the x sub n, and form a unitary matrix or the deck or the adjoint of the unitary matrix, and use that to transform the operator. And once you do the transformation, A will be diagonalized with only the diagonal lines are non-zero, other terms are zero. And then the same for the A deck using the same transformation matrix, and the diagonal lines become lambda 1 star, lambda 2 star, and lambda n star, and the rest are zero. And so that is similar to the Hermitian matrix result, but then the difference is that the diagonal lines, the values are not the same for the two operators. They are complex conjugate to each other. That's the result for the normal matrix, and but otherwise they're similar. So you can go through the process of diagonalization using the eigenvectors and form the unitary matrix and do the transformation of the matrices.